All right, let's get started. So everyone's got their homework back. I'm halfway through grading the projects, and I will have my printed reports and everything to you. I doubt I'll have them on Thursday, but I'll have them on Tuesday for sure. Next Tuesday for sure. The ones that I've done so far have been very well done. I think there were 3 perfect scores and 148.5 out of 50. So the groups. I don't know what that means for the other 4 groups, but the first 4 groups did outstanding. So, all right, let's go. Let's get to 5.9 here. So I wanted to, have you had the opportunity to go on to your, I'm bound to have it here somewhere. If I don't, I can just go on to Blackboard. So if you've gone on to Blackboard and looked at this MIP screen sheet yet.
I may have. I don't know.
Okay, so I would highly, highly recommend when you get the opportunity to go under Content, use your own password instead of mine, go into 385. So under Content, down here I have reference files. So I've provided a number of files that would be helpful for you. This is where you found some of your C stuff. This is where for example, I have the original MIPS paper that Patterson and Hennessy wrote. They kind of broke down everything. So here you find all this, the compiler-driven encoding of the microengine. That all comes from this paper here. And but the one that's going to be, and this is the actual paper that Karnow wrote when he actually proposed Karnow maps. So give us a split second to load here. And so you can actually tell, what he was doing and why he decided to justify it. You can kind of go through here. He is explaining it. And then if this is the one that I think it is, at the end, somebody came by and tried saying that his method was dumb. And then at the end, let's see, where exactly is it? So we're trying to find, well, it's somewhere in here, but he's basically said, this guy comes by, Caldwell from MIT, and says, your idea is stupid. And he says, hey, actually, basically the summation of Karnow's retort is, hey, you should learn how to read. Which is correct. You completely misread the paper and decided to go, hey, look at me, I can't read, and that's what happened. So it's always fascinating to see those kinds of things. But the thing that will be very helpful to you, I should change that to 7.25, is this MIP screen sheet. So for those of you who have the textbook, it's the first page, that green fold out, and you can go in here and you can actually see, I can zoom in here, you can actually see we already have covered add, right? And so everything you need to know about an instruction is right here. You have what it's like in MIPS assembly. You have, this is Verilog. We won't be covering Verilog in this course, but Verilog is a hardware description language just like VHDL, and kind of what you guys are doing similarly in C, where you're deciding the AND gates and then building the full adders and building the multiplexers. And so now at this point, you've now built an entire arithmetic logic unit, right? And so next assignment, you're actually going to be building SRAMs, and you're actually going to be building memory elements. And then the final project is putting them all together, and you've built a full computer from C. So here, we know RS, RT, and RD, right? So you add the 2. So basically, you take 2 things from registers, you add them in your ALU, which you now have, because you have your opcode. Your opcode function value 20 hex, and it's stored in the destination register. This will be very helpful in being able to understand how all the instructions are actually working. So today we're going to be talking about this add immediate instruction and what that means, and we're going to eventually go into more detail about what's physically going on there. So we've already talked about immediate type instructions. We're talking about branch equal, branch not equal, jump, link, jump register, and load word and store word is down here. The store word instructions, right? So we're going to be going over all of that. And so you can actually see here the TGO that I gave you guys for the registers is right here. Now the reason why I consider this so important is we're going to be at the, today we're actually going to be going over this big problem where you're actually going to have a main function and we're going to have a called function and we're going to actually see what's physically going on with pointers today. So a lot of the feedback I got is like I'm still struggling with pointers a little bit. So basically once you see physically what's going on, hopefully that'll clarify some of the confusion. But then you see you have variables for inputs to the functions, your temporary values, saved temporaries, which you actually have your variables, and you'll be dealing with mostly these. And you'll be also dealing with the return address. So basically return address is you have a function, you get to the end of the function, and you want to go back to main. The return address is the instruction, the next instruction after the call. So we're going to show an example of that today. And we won't be messing with OS kernel, global point stack, or frame pointers in this course. You'll be learning that a little more in your computer organization class. So just bear in mind that that's in there. So you're going to see, also today you'll understand what return 0 actually does. So let's get out of here. So this is very useful. And then the second page, IEEE 754 format, how it's actually done. You got single and double precision. So you know the difference between float and double. So you now understand physically, single precision format was 30 to 22, or 30 to 23 was the exponent, and then 22 down to 0 is the mantissa. In double precision format, 6-bit 63 is the assigned bit, 62 to 52, so it requires 11 bits. So it goes 2 to the 11, so that's 2048. And then 51 down to 0 is your mantissa. So that's why when you did I think there are 2 groups that did the creativity challenge, and you actually printed out the float and you put in that number, and it actually gave you 1 pound infinity. That was why that's doing that, because you can't go above. You can go above that using doubles, but since we're doing 32 bits and we're limiting it to a 32-bit architecture, that's why I limited you to float and didn't permit doubles. Okay. So, yeah. Okay, so here what we're going to talk about is this add immediate instruction. So here we have, this is 5.9, translate the following C code into MIPS, register transfer language, which is the first line in your green sheet, then MIPS assembly language, then the machine code. Assume G has already been loaded into S0, H into S1, and F is into S4. So we're going to learn why that assumption is important later today. So first things first, we got to remember order of operations. So you have to have the result of G of H plus 5, right? Here first. So when we did add, we take 2 values from registers, add them, and put them back into a third register. In this add immediate, this is where we have some sort of constant value, 5. If you remember, what is the format of an I-type instruction? Or have we? RS, you're on the right path. RT, and then?
The big end.
Yeah.
What do you call it?
It's called,
I don't remember.
what's the name of the, I just said it's add immediate, right? And so that value is called an immediate value. It's a 16-bit value that corresponds to some sort of number. So for example, if I'm doing a load word instruction, I have a base pointer to an array, and I need to add the offset. Well, the offset is just some number that we've calculated. So that's how we do that there. So that's how immediate instructions are: data transfer instructions, load word, store word, add immediate. So we have some T0, which I've put this down there, but those of you in the back. So basically, that's called add I, and then I can use one of my temporary registers to store the intermediate value. Do not store it in F. Why don't we store it in F?
That's your register.
Yeah. Xavier hit on it. You're dancing around it. Xavier hit it on the head. You never tell the code to do H plus 5 equals F, correct? So you can't do what the coder. You have to do what the coder tells you to do. And sometimes, as your compiler told you, sometimes it was painful, right? Like it would. So first thing we gotta do is add I, and then we're gonna store it in T0. So the first one we do is we're gonna have T0, and then it's gonna add H. H is in S1, so we call that S1, and then 5. So S1 plus 5 is going to go into T0. So that's the format of the first instruction. And if we scroll up, you'll see that the first answer is, in fact, add I T0 S1 5. And this in assembly, this dash dash here, that's identical to comment. So in C, you have comment or this, right, where you're commenting. In the assembly, you're going to find that this is your commenting. So here I've commented, and then I've actually given the MIPS register transfer language on the right-hand side. So our T0 is equal to, so the register value of T0 is going to be equal to the register value of S1 plus 5. And then from there, S0 is H. H, right? What? S0 is G. Okay, so S0 is G, and then we add the result of T0 here. So basically we're just taking this value and adding it to that value and storing in S4, which is F. So does that make sense what I've done so far? All right, so next step is to take these two instructions we have and convert them into these values. So we go back to our MIP screen sheet, and we go to add I. Now, it doesn't have a, this is where students sometimes get confused. So this is why I want to refer to the MIP screen sheet here. So let's look at the difference between add and add I in the MIP screen sheet. So here I have specifically, let's talk about, it says it's opcode / funct, and you notice that there's no second value for add immediate. It only says 8 hex. So what does that mean?
It's the same for the opcode and the function.
No. There you go. That's the answer I was looking for. There is no function. Why? Let's go back to the immediate format.
Because it's not the immediate form.
Yeah, opcode, RS, RT, immediate is the last 16 bits. There is no function. Because we need to use those 16, and we'll learn how to make that. Usually by now I've gotten the question, wait, if it's 16 bits, how do I add it to a 32-bit value? And I do the I believe thing and everyone giggles. No one asked that yet, so I'm guessing you guys are figuring that out. But eventually, you have this value that you're going to put in your sign extension immediate and add it, but your opcode is just 8 hex. So it's going to be 0, 0, 1, 0, 0, 0. So going back to our problem.
What is the 1 and the 2 in the parentheses?
That's a good question. I don't know.
Does that have something to do with in Verilog?
Well, this is the Verilog code. Two and 7. I don't know. I'll look into it. Next class I will have down here, hey, look at that. Hey, here we go, I found it. 1, may cause overflow exception. Why would 1 and then 2 is sign immediate equals 16. It's just basically telling you that that's the 16-bit value. So why would 1 apply to add and add immediate? Think back to overflow. Yeah, so you can have 2 values and you could overflow and make it refire. Yeah. So basically, to answer your question, the parentheses are possible errors or possible notes that are required. So sign immediate, you may wonder what sign immediate 7 to 0 is for load byte, which you won't have to deal with you'd only load 1 byte instead of the full 32 bits, but you'll be doing the 32 bits in course. So these are the 7 comments. And then here's your instruction formats right here. So here, just like we did before, function, you have the last 6 bits there. RSRT-RD, shift amount, RSRT, 16-bit immediate, 26-bit jump address. So going back to the lecture notes, we now know that add immediate is 8 hex, which is 001000. We know that S1 is RS, so we take this value from S1, we put it here. And then our destination register is T0, which is 8, which is here. So that's 16 plus 1. S1 starts at 16, so 17 is S1. T0 is 8, so we put it here. And then to save you guys some time, this is 16 bits. You see I have a little ... here. So on a homework assignment, on an exam, it's a little time consuming. 1, 2, 3, 4, 5, 6, 7. As long as you put the last, it indicates 5 because it's plus 5. So that's an add I instruction. And then you're going to have add. Remember, opcode for add is zeros. And then S0 here. So that's RS. So we get rid of this. Again, we go to RS is 0. So here that goes there. RT is this guy. And then RD is there. So you got S4. So you can see this is a good diagram that describes the difference and what the machine code is versus the assembly language. Remember, like if you talk about, if we go back to section 1, I talk about there are these design compromises that were meant to improve performance. Once you start getting into how this machine code flows through the architecture, you'll understand why they put it this way to keep with normal assembly language, but then switch to this way in order to improve design flow. If you recall, they had to make those compromises to improve performance. So this is where it's starting to happen. Okay, so that's where the problem ends. Does anybody have any questions about add and add immediate R and I type instructions? Yes.
How did you get the RS and the RT?
RS and RT are the source and destination register for I type instructions.
How did you get the machine code there?
All right. Let me ask you, how did I do it? Since I just spent.
Oh man.
Where do these values come from?
From the address.
And so where do you get the register values from? When I spend the first 5 minutes showing you guys.
But the green sheet.
Yeah, so we go back to the MIP screen sheet. All right, so you're going to direct us, Joseph, to the answer to your question. So we go back to our MIP screen sheet, right? And so where would I want to look up the register names and numbers? All right, so we go to our register names and numbers, probably over here. Have more confidence in yourself. All right, so which two were we looking up?
The T0, row and trouble.
Right? And so it's 5 bits, so it's 0, 1, right? And then S1 is 16 plus 1, which becomes 1, 0, 0, 0, 1. Yeah, there you go. No, I knew you knew the answer. I just wanted you to walk through your question. Yeah. All right. Any other questions before we move on? All right. So this is where we start getting into memory stuff. So this is where load word and storage come into play. Load word is you are taking an element from the data memory and putting it into a local copy of the register. We've find a formula there. Load word instructions are instructions that take an address calculated by the ALU. So what we're going to do is we're going to have the sign extended value and a base pointer that's held in one of the saved temporary registers. add them together, and then remember we have this byte addressing, right? So everything's plus 4. So 0 is element 0 in the array, 4 becomes 1 in the array. So if a base pointer points to, like, think of it this way. The analogy I like to use is a street. So you have this data memory element, right? And you say we need to get to University Drive or whatever. And so this is where you turn on the University Drive here. So every house, we'll call the byte addressing houses, represents, if you want a mailbox, remember that it's not like 0, 1, 2, 3. Sometimes it separates like 100, 200, 300, or 81, 0. Right, the road I grew up on, 8100, 8200, 8300, so forth, right? And so they're blocked off by hundreds or tens or 50s or whatever unit they use. In MIPS, it's byte addressing. We say it's 4 because each byte represents one element. Right? So you have 8 SRAM. And then you put 4 of them together and you get 132-bit word. And that represents the value we're getting from the data memory and putting back into the register. So that's why so 0 through 3 is going to be the first element. 4 through 7 is going to be the next element. 8 through 11 is going to be the next element. 12 through 15 and so on. And that's from the base pointer, which is stored in a register. So that, getting back to our definition, it's an address calculated by the ALU and loads the value from that address into a register specified by the instruction. So load word instruction is an I-type instruction. So this is from the MIP screen sheet. RT, where the register value for your destination function, getting back to Joseph's question, is equal to the memory address. So this M stands for memory address. The memory value found by this address, where you take the value in register RS, add the 16-bit immediate value, get the element from memory. That value is then stored as the value of register RT. And in assembly, that's what it looks like. Now here's what this means. Let's say we have I equals, and we're going to give example problems in a second here, but we have array of 3, where S0 has I and S1 has the base pointer to the array, right? So what this means is I'm going to have load word S0, and then this sign immediate value, we're going to use byte addressing. So I want the array value of 3. So what's that assign immediate value going to be? Think back to the analogy I just gave. If I have byte address, so each memory element in data memory is a byte, and MIPS architecture is 32, so it's a word. So how many of those bytes do I need to make one word? 4. So what's the value that I'm going to put into the instruction here if I want the third element in the array?
The last.
Not the. 4 is each element in the array takes 4. There's a reason I'm spending so much time. This is a very common confusion among students. So if I have 4 in each element, so element 0 requires the first 4. So 0 to 4, 0 to 3, 4 to 8 is 1, 0, 1, 2, 3. So what's the value? What's the value that I want? You guys you're counting on your fingers. There's a simple multiplication I want you to do. How many does each one take?
4.
12.
Oh.
There we go. I knew someone would do it. Oh. The number in the array times 4. I'd rather you struggle with it now than on the exam. So this becomes 12. So that becomes our sign extension immediate value. And then our base pointer is S1. So whatever value is in S1, we're just going to go here to our data memory. Here's where's where S1 points. So we have our pointer to the base element of the array. And then when you do this code, all you're doing is saying, you're taking it down to the compiler level and saying, tell me the number of blocks I need to go in memory to get the 4 blocks that I want. Right? So this is what a pointer physically is. A pointer has the base element of the array. Now go 12 and grab me the next 4. So 12, 13, 14, and 15. And now you're getting those elements and loading them into the local register. So if I have 4 blocks, and so now let's discuss what a pointer is when I'm passing by reference for just one word. Right? So one word means it's one 32-bit value, it's one Boolean, one integer, all that. Right? In MIPS, it's going to be different value in a CISC architecture, but we're in a RISC architecture, so everything's 32-bit. So what would this value be for your sign immediate if I have a pointer to a memory element in data memory? I'm pointing to the memory element, and this is the memory element I want right there. That's what the pointer is. The pointer is saying the memory element is here in data memory. So what's my offset going to be? I can see a couple of you want to say it. What's that? No, but you're close. 0. If you're pointing right at it. Yeah. So that's what a pointer is. If I'm if when you have some function, right? We'll call it foo, and you have int star a. What you're doing is you're going to do a load word, because this is a pointer that's stored in a saved temporary register to an element in data memory. So you just do load word 0, whatever this register is, and store it in a temporary register. And then every time you update the temporary register, you're going to do this next thing, store word instruction. So you're going to update the data memory immediately, which is why that's how you pass by reference. So let's get to the store word instruction. Store word is our instruction. Store word instructions are instructions. Let me scroll up here so those of you in the back can see. Store word instructions are instructions that take an address calculated by the ALU. So far we're doing the same thing. And stores the value from a register specified by the instruction to that address in memory. So now we're doing the exact opposite. We were going into memory, we were grabbing the value from the data memory and putting it to a local register. Now store word is we're storing a value from the local register back into data memory. Now why would you think it would be load word from data memory and store to data memory? What's the importance of having data memory kind of be considered the home and the local registers kind of be considered like the temporary copies?
You use registers for more than that operation, so you want your
right. You're on the right path. You're on the right path. But what is okay? I might not. So they're made of SRAM, these registers, right? And eventually, data memory is made of cache, and it's eventually going to go to some sort of disk. So what's important about registers being SRAM? What's the word? It starts with a V.
volatile.
Volatile memory. That means eventually you want to store things as often as possible so you don't lose your information. Computer turns off, or for some reason I would just turn off my computer. Everything in the local registers, everything in the cache is lost, unless you have something in your operating system, which more and more operating systems do now, where they make sure that it saves everything. If you're old enough to use computers in the 80s and your computer just turned off, you're like, oh well, crap, everything's gone now. And I don't even have an internet. What am I doing? So you can't even back anything up. So store word, you have 2 and 11 here. So this is going to be 2, 9, 10, 11. So it's going to be 2 and B, hex, right? How many of you seen The Martian? That is not The Martian. How many of you have seen The Martian? No one? Okay, so none of you would understand the reference that, part of how he manages to get off the planet is because he has a thorough understanding of hexadecimal. I recommend you see that movie. It's a very good movie. So anyway, the plot point is that they figured out how to use the pathfinder to circle around to communicate back and forth between NASA and where he is on the planet. But he realizes that he can't use 26 letters because it would be hard for him to figure it out. So he reduces it down to hexadecimal, and they can convert the hexadecimal to ASCII. So this is ultimately a binary version of hex. So if you went to your MIP screen sheet, we will see that it's going to be 2B hex. And actually, there it is right there. I've copied it over. And so the other things, you have store word, we have S0, and we'll call it 8S1. So I'm taking a value from the save register, finding the base pointer to the array, and now which element in the array am I putting it into? If I have the value of 8, which array element am I entering it in? 2. Who said? I heard someone say 6. No one said 6. Okay, it's supposed to be 2 because the 8 divided by 4. But if someone had said 6, I was just going to figure out what the concept error was and help them fix it. So, all right, does anybody have any questions on load word and store word? We're going to go over some example questions on how they're implemented. All right, so example question 5.9. So now we have our same kind of setup question where we have the base pointer of array A is stored in S5, the value of C is stored in S3, and the function that we're doing is A of 8 equals element of 7 plus the variable C. So I've done a lot of describing of what's going on here. So this is basically kind of what I've told you. So the first thing we need to do is we need to figure out our offset and base pointer. So the first thing we're going to do is we look at this value and go, okay, I need that value here. So I can allocate a temporary register here. So I'm going to say T0. And so what's my, so now I need my offset and my base pointer. So what are the two values I'm going to put in here? Yes, which is?
That's your offset.
Which is 28. Yeah. All things you said, Joseph, were correct, but I wanted the number. And so what's the value I need to put up next to it? Something here. What am I adding the offset to? Yeah. So where's that value stored?
S5.
S5. Good. The base of the array is stored in S5. So that's our first instruction. We are taking the base pointer of the array stored in S5. We are adding 28 because we need 28, 29, 30, and 31 to get that word from our byte addressing. Put it together. Now it's one 32-bit element. For those of you who are thinking in C code, oh, hey, now I know how to combine arrays of smaller elements into one larger one, right? Using for loops. Do that, and then store it into T0. So that's our first instruction. So now, we have to add these. So what do you think this instruction should be? Remember, S3 is where C is stored. And we have the value of A of 7 stored in T0. Someone besides Joseph, Xavier, and Colbert. If I don't get one in 5 seconds, I'm going to pick one. All right. Who looks like they really, really don't no one. Olivia Williams. Pull your hat down. I'm definitely going to call you on that one. Okay, so what do you think the instruction should be?
Well, let me just repeat the question first.
Yeah, what is, okay, so we have our first instruction completed. And so now we're getting this, so we complete our load word, we've got our load word in temporary register. And so now I need to complete this addition. So my question is, should this be in the MIPS assembly language? Given that we have S3 is where C is, and T0 is where A of 7 is now. Can you close the door in the back, or you don't have to shut it all the way, but just enough to keep their racket out. Thank you. Perfect. Okay, fine. You're all trapped here. So, what is the format of the add instruction? Yes. Mm-hmm. Correct. Mm-hmm. So what is my RS value? Order of operations. Where's this value stored? Oh no, well, that's this value. So you're on the right path. So that's 3 here. So we have our RT value. So where's this value stored? We just got it in the previous instruction. Bingo. So T0 plus S3. And then this is where the trick part comes in. Where should you store it? Okay, that's good. That's good enough, right? So we can reuse T0. We can reuse our temporary registers, right? Because once we're done with it, we can add T0 and S3 and store it in T0. Because once we no longer need this value, we can just overwrite it. So now we have all of this stored into T0, and now all we need to do is store it back into memory. So who's going to be my victim for the next one? Suddenly everyone's making eye contact, and let's see. Tahir. Store word instruction. I have a value in T0, I need to store it in A of 8. So first things first, I'll write the first one out for you. Mm-hmm. So what value am I storing?
I'm not sure.
Okay, so I have the solution to A of 7, right?
Right.
And where did I store that where did Olivia store that in her previous instruction? No, well you're doing that. Where did she? What did she? Temporary register, right? So we're going to take that, and then we have to do this instruction's version of that for the stored location. So A of 8, what's that going to be?
0S4.
0S4? Okay, so 32. Why is it 32? Your classmate's helping you out here.
8 times 4.
8 times 4 is 32, right, Tahir? All right, so 32, and then Tahir, what's my last thing I need to do? If I'm storing it back into A, where is A stored initially?
Initially,
Say it. I know you want to say it. Just say it.
S5.
Yes. You gotta learn to trust yourself. Better to make mistakes now than on the exam. See? So now you have done the same thing. This is the identical to a pointer, right? So you've taken a pointer to an array, you got the value from the pointer, you added it, and then you stored it back using the same pointer. Okay. Does that make sense? Okay.
I guess instead of overriding T0, you could have used any of them.
Yeah, that's a very good point. You could have used any of those on an exam if you wrote T1 or T2. Any of those, you get full credit as long as it works. That's the compiler optimal solution. Now, this is where we get a little tricky, and so Olivia and Tahir are going to be very happy that I picked on them first. So 5.10, so that's your solution as we have just drawn up on the board. In 5.10, now you know you have code where it's not a value, it is a variable. So this is where it gets a little nasty. So I have the same problem, except instead of giving you 8 and 7, B and D are variables. So A is stored, the base pointer to the array is an S5, B is S1, C is S3, and D is S4. So if we're using, okay, so basically you're going to have, let's say B is 5, right? So what's my value that I'm going to want to put in there going to be? 20. People are starting to get more confident in the fact that they can multiply by 4. So if I want to multiply by 4, and we know from the previous exam that sign multiplication can require a lot of clock cycles, but I want to do it efficiently, what instruction would I want to use to multiply that value by 4? Shift left logical, correct? I think that's the I've asked that question. This is like the 8th time I've taught this course. That's the fastest I've ever gotten the shift left logical answer. Sometimes I'll even have it right there, and people just go, oh no, don't call on me. The shift left logical, because remember we went over that before, which multiply by 2, and you all have actually coded that already. So there's going to be places in the data path where you just have a shift left logical where you put the value in, you hard code in 2, and then it puts it out for you. So you're going to shift left logical. So we're going to use temporary values. We're going to shift left logical T0. B is in S1. And you're going to do 2. So now you've multiplied it by 4. So now you have your offset variable. But here's the thing. In the load word instruction, the signed immediate value is some sort of constant. It's still not a constant because we don't know it until you've actually run the code, right? So we have to do one other thing here. Now we have our base pointer to S5, and we know the offset, but it's a variable. So what I can do is we're going to create a second pointer. So we're going to add, and we're going to have T0, which is our initial offset. We can reuse T0, so we're going to add it here. And then we have our base pointer to our array, which is in S5. And then our offset, which is T0. And then we store that numerical value in T0, right? So now what value does T0 have? Correct. So now we are pointing exactly at the location of memory where the element we want is, right? So now if I want to load this value into a temporary register, what's my instruction going to look like? So I'll give you a hint. We can reuse the temporary register again. And then I have some value that I want. Let's see. We're still jotting down. So any ideas? Since now we're pointing exactly where we want, and the register, and we have the value stored in T0, and we're doing a load word instruction. 0. Very good, very good. And then what's this other guy going to be? T is 0. So now I have A of B loaded into T of 0. So what's my next instruction going to be? You can even reuse T0 again. You can do T1. I'll do T1 just to say you're allowed to do it. T1 of T of 0, order of operations. And what's the last one going to be here? S3. So now I have my result in T1. Right? And so, yeah, very good. Store. So how are we going to do store word here? I have A of D, right?
We need to do the same thing we did with B2.
Exactly right. So let's do it. So we're going to do the same thing. So shift left logical, and let's just we'll do T2, D, which is in S4, and 2, which is the same as multiplying by 4. And then we're going to add T2, S5, which is the base pointer to A, and T2. And then store word, T0, which is our initial value, 0, T2. So this is pointing to A of D, and this is the sum of that value. So now in this problem, and I'm going to scroll down and show you the type solutions in a second, especially for those of you reading it later. But now we have, to do this, we had a pointer. We created a second pointer. We got the value. We stored it in a temporary register. We added, and then using that same pointer again, we created a pointer, stored the value, and then left everything alone. So this is what pointers are physically doing. Does that make sense? We'll be going over another, I think 5.11 is the big example. All right, so and so the code solutions are here. And so that's where the first three that we did. So shift left logical, add, load word. And then we actually did the addition here. And then we did the last three there. And so I also give these values here. We can go over all of these here too. So here we shift left logical. It's an R-type instruction, so we have opcode is 0. Its function is also 0 if you look in the green sheet. We have T0, 0, 8. And so we shift by 2 here. That's where our values come in. And then same thing, this should be, so it's RSRT. Now here's an interesting, let's go back to the MEPS green sheet and see what's going on here. So we go to shift left logical. It's an R-type instruction, RT and RD, right? And we know shift amounts the 5-bit value, and it's 0 and 0 hex. But notice how there's no RS in this instruction, right? So that's why when we go back to our solution that we have here before, if we look at these two shift left logicals, this instruction here and this instruction here, notice how RS has a 0 value. In theory, you could put any value in there you want. It could be all ones, it could be all zeros, it doesn't matter, because the opcode is going to control the flow. So it's just going to say, I only need RT and RD. And in both of these cases, the shift amount, so this is temporary, this is S1, right? Here, same thing, we have S4, which is this guy, and T1, which is this guy, right? And then the shift amount here and here correspond to this. And then remember it's 0/0, so our opcode is 0 and our function is 0 for both of those instructions. So for second one, we used add. So remember it was 0 and 2 0 hex. RS was T0. RT was S5, and they stored it in T0, so that's this value. Our shift amount is 0. For the third instruction, we used a load word. So opcode was 2 3 hex for load word. T0 and T0, so they're both 8. And then our offset was 0, so it's going to be 16 zeros. Then we perform the addition. So again, add 20 hex, T0 plus S3. So this is 16 plus 3, so hence it's 19. We're storing it back in T0. Shift amount is 0 there. And then we are doing, so we brought over this shift instruction. 0, T1, 8 plus 1 is 9. 8 plus 1 is 9. And so we're adding this value, and I made a mistake. This should be 1, 0, 1, 0, 1, and this should be 0, 1, 0, 0, 1. Right? So this is RS, which corresponds to this guy, RT, which corresponds to this guy, and RD, which corresponds to this guy. In fact, if I have that there, I can make the correction. That'll give us just enough time to finish the last few TGOs and example questions. So let me go into my lecture notes, lecture section 5, and I will make that correction for you right now. So this one, so this was here, so this one should be there, and this should be 10101. Correct? So, professor holding himself accountable, he updates his lecture notes. All right. So, does anybody have any questions on that before we move on? So now we're going to start talking about these concepts of branch and jump instructions. Branch is what we're using if we have if statements. So I have a certain number of instructions inside an if statement. And if the condition is not met, you want to go past all of those, right? That is what's known as branching. Jumping is I can jump to any instruction that's indicated in the 26-bit immediate value, right? So in order to do these, we have 3 types of instructions that are used. Branch equivalent, branch if equal. If they're equal, we're going to branch past the instructions. So if that's the case, that means it was I does not equal J is in your code. Branch not equal, we branch past the instructions if they're not equal, meaning if I equals J. And then we're going to use this set less than instruction, which you guys have already written the code for, to be able to indicate whether or not the value is less than, so if the first RS is less than RT, set the value equal to 0 or 1, based on whether it's less than or not. So jump instructions, JINSTR is just your typical jump to this 26-bit value, which we'll show you how to make that a 32-bit value in section 7. JRRA means jump register. This means there's a 32-bit value. You're going to jump to the value indicated in the register. And then jump and link is what's known as, so it jumps to the indicated address. So you can copy the program counter, so to the value of the register plus 8, and jumps to the program statement at that label. So you're going to add this value to, so you have this address. So here you're going to make it 2 instructions later. There's a specific, value for this, being able to jump to and from functions. So I've given, want to go in a little more detail about what exactly are branching and jumping. So here I've given an example of while I is equal to j, I equals a of j, j plus plus. So here we're going to do some sort of comparison, and then we get down to here, right? So branching means if I does not equal j, then I just want to go past this code entirely, right? So that's a branch. Jumping is what happens when I actually go in here, I do the code, and then I want to jump back to this instruction. That's jumping. And also, if let's say this is the end of a function, if I have return I or something like that, then I would go back to main. And so I've kind of looked here. Okay, so I want to, this whole thing, I want to kind of explain something that's going to be a big I believe button moment. So what happens is, in the physical MIPS data path, you're going to take the value of the instruction in that 16-bit value. You're going to do a shift left logical to multiply by 4 because the PC plus 4 is going to be the same byte addressing. However, the value that you're actually going to store is just going to be, so if I have 10 instructions, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's going to physically multiply that to 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, right? So all of this right here, basically all I'm saying is when you see the instruction counts are 1, 2, 3, 4, 5, and you know they're supposed to be 4, 8, 12, 16, 20, it's okay, relax, we'll get there in section 7 when I show you physically how it's done. That's a big concept there. I just wanted to go over that before. So jump. So basically here I've shown you an example of how this instruction works. And we're going to be going over some TGOs to kind of go into more detail. But here it's I equals j. So the first thing I did is I did a branch not equal. And then we did the same thing. We had to get from the array, so we did the shift left logical. We loaded from the base pointer, and I added j plus I equals a of j here. And then we incremented j plus plus. And then j, now here's the key thing. Jump 64 means that it goes back to this instruction and does it again. Same thing in the jump instruction. There is a shift left logical too. So that function that you guys wrote, you'll be using it multiple times in your final data path. But here it jumps back to 64, so that's a jump. Branch not equal, that should be 1, 2, 3, 4, 1. Yeah, okay, so that should be 5. So that means that's the whole point of me making that I made the same mistake. So the way the data path works is when you have PC, your program counter, where this instruction is, the first thing it does is that you're going to add plus 4 to go to the next instruction. So we've already added 1 automatically just to go to the next instruction by default. So then we're going to go 1, 2, 3, 4, 5 to 70. So for right now, just in the big example problem we're going to be doing here to finish up the lecture, in my comment, I commented extensively how it's done. So here, this is an important TGO. I've gone over all 4 instances. I is less than j. I is less than or equal to j. I is greater than j. I is greater than or equal to j. How to use MIPS instructions to be able to do all of these things. So for I is less than j, first thing you're going to do is you're set a temporary register. So all of these assume that S1 has I and S2 has j. For if set less than, if I is less than j, 1 if it's I is less than j, 0 if it's not. So in this case, we're looking for branch if I is equal to j automatically, and then we're going to compare this value. So here, if I is less than j, that means we want a 1 in there, right? So if we have a 1 in there, that means we will meet the condition. So we do not want them to be equal, right? So if it's 1, that means it's met the condition. We also want to branch automatically if they're equal, because it's not I equals j, we want to go past it. And then if t is 1, that means I is less than j, so therefore we want to branch if it's not equal. So if we compare this with this one here, we do the same thing, except we do this, since it flips, the compiler, S2 and S1, is j less than I? And then we branch automatically if they're equal. And then if it's 1, that means we have met the condition, so we do not want them to be equal. So this means if t of 0 is 1, that means j is less than I, so we do not want to branch. For this one here, for if I is less than or equal to j, here we set t0 is 1 if j is less than I. So if I is less than or equal to j, then that means the opposite when we do want to branch just means if j is less than I, which is why I've done this little thing here, branch. I wrote the conditions where we want to branch because it's the exact opposite of the condition in there. So branch if j is equal to I. So if j is less than I, then it's going to be 1 in t0 if we use set less than, correct? If we do it in this order, where if j s2 is less than I s1. So if it meets that condition, then we can say branch not equal 1 and 0. Then if it's 0, that means we've met the condition to stay in the if statement. And last but certainly not least, if I is greater than or equal to j, that means we want to branch if I is less than j. And so we have set less than S1 and S2. T is equal to 1 if I is less than j. And it should be not equal. That means if we have a 1 here, that's correct. Then we want to compare those values and do the result. So does anybody have any questions about this? All right, so, and I did a little brief review. We got 10 minutes. That's enough time to go over this last question. V0 through V1 are return variables. A0 through A3 are instructions, are variables that can be passed to a function. And RA is your jump return address, as we've covered earlier. And so we're going to break down a fundamental C function. And hopefully after we've gone through all of this, you'll have a much better understanding of how pointers work, so that way your projects will go smoother. Okay. So let me scroll here. So this is our problem. We have a C code here. We've allocated this function test function, where it passed as int star array, int star 1, and int b. So array is just an array of integers. S0 is the register, the save temporary register. We have the base pointer to that array. S1 is first, which we've declared in main. S2 is second, which we've declared in main as well. We call this function test function, where we pass the array. We pass a reference for set first, and then second as well. So we're going to be calling that function, and then in that function we have, we're actually calling some registers here, right? So we have pointers, we have if statements, we got all that stuff going on. And then we return and then we come back here and we perform a 3-part addition. So this is about as complicated as it could get on an exam question. So let's go through this. So the first thing is we're going to start with our value here. So we set the array pointer. So the first thing we do is we've already allocated the values in the register, right? So we have these, this is in data memory, and these values 0 and 3 are in the register. So the first thing we're doing is we're actually calling this function, sum, right? And then, so the first thing I'm doing is I'm going to A0. S0 holds the base pointer of the array, right? So what I'm doing is I've done an add I instruction where I've just basically copied S0 into the first argument. So the base pointer is now in the first array, a function argument. And now, okay, so I want to, before we get to instruction 2, I want to point out an important caveat I've put into the initial. You may load any pointer to an integer to any location, as long as it's after the first 8 elements. So here we have a 7-element array, right? So 0 through 7. So any other element past there, you can load it. So what I have done is I have loaded the 8th value and said that's where I'm holding the pointer to first. So going back to this second instruction here, set arg1 is a pointer to 8. So I'm actually saying 8 times 4 is 32. So I'm actually saying 32, 33, 34, and 35. I'm going to store a copy of S1. Should be S1. S1 into A1 there, right? So that's where my pointer is. And so what I've done is I've loaded, now that I have this as my pointer that contains the value 8, I can just simply do a store word where I have, oh no, that's correct. So the reason I have A1 there is because in the problem I state, assume all register values hold 0 unless specified in main, right? So here it's 0 plus 32 is going to be equal to 32. So now we're pointing to a location in memory that's A1. So now I'm using the store word to copy S1 to that address. So now I've taken the local register copy and put it in data memory. So now you have a pointer A1, and you now have a copy in data memory. And that's the value that's, when we get to the function, that's what's going to be changed. So every time we're going to update A1, and then before we get to the function again, we're going to load that value from data memory and put it into the local register. So that's how pass by reference works physically. The next thing, second, we're actually just taking S2, adding 0, and putting it into A2 there, because we're passing by value. So any value we change in A2 doesn't affect S2 at all. So that's what pass by value is. This is pass by reference. So that's the difference. So by doing the ampersand, you're actually physically doing instructions 2 and 3. And then here is add I. So I'm setting the return address. Remember, the value register 0 is stored as 0, right? And I determined that the next instruction in main is going to be 6. So I just tell it, you need to return to instruction 6. I'm sorry, it should be 7. There should be 7 here. Jump to instruction 7 because you're going to do the rest of this, right? So you're going to jump down to 12 to do the function. But let's complete the rest of main here. So we've jumped back to 7 because I've been smarter and corrected my code. So this should be 7 here. And then I have this value here, V0. V0 is my result from, because I've allocated the sum value. So sum is in S3. So I've taken that result, added 0, and put it in S3. So now that's how you physically return a value from mains, from function, sorry. So function V0, S3 is where we had sum, and then load word A1 is where the copy that all this we've updated A1 down here, stored into S1 right here. Or this should be, I'm sorry, loaded into S1. So now we've updated the value that we passed by reference by a pointer. And that's why when you call a function in main and pass it by a pointer, the value's updated properly. And see how we don't do this with S2, because second's never updated? We can make all the changes to second we want, which I show you down here, but it doesn't matter because we don't pass it back in main. So you pass by value, you preserve the value, you pass by reference, you can change the value. So then here, we added sum plus first, so it's S3, which we've updated here, plus S1, which we've updated here. And that's stored in a temporary register. And then seconds, which we have not updated, T0 goes back into S2. And then jump 0. Notice how our instruction starts at 1? Jump 0 jumps before that, where you'll have some sort of instruction, which we'll cover later in section 7, to tell the operating system that you're done with the program. So you're actually jumping to 0, hence return 0. So now let's go into our function. We have a couple minutes and we'll finish this. This will be the last thing we cover. So here, we're actually going to, let me put the creativity challenges up here real quick. I have 2 creativity challenges. Remember from last lecture we had the muxes? I showed you use the multiplexer and the 3 variable input. And you did a problem. Design 3 of those problems you're on and create the solutions for them and have them to me by Thursday. So that's a creativity challenge. And then you're going to do a similar problem to this by next Tuesday. Come up with your own solution, submit that. That's another creativity challenge. So I will post the solutions to all of those. I'll correct your if they have mistakes and post them to Blackboard, and you can all use those to help study. So in the function, we have here, we initialize sum to 0, and then we get this. We have a pointer to first, so we're actually getting the value from A1, loading it to a temporary register, and see how I have this first equals first plus 1. What we're going to do here is we're going to do a store instruction after every one of those to update S1. So here, sum is equal to 0, but that's fine because we've assumed that all the variables. So we take the value from A1, we load it into T0, we multiply by 4 to get our shift left logical for our array, and then we add those values and we get the value from first and the array. So array of the pointer of first is now stored in T2. And then T2 is our base pointer. We can load it in a third temporary register. So now we have the actual physical value. And then we do from our TGO branch equivalent. We want to branch 6 instructions. So I calculated we're going to 23. If we branch past all of those, we're jumping to the return, and the reason why is because here, if it doesn't work, we're just returning sum. So and the way I calculated that is here, 16, which is where we're at, it increments 1 automatically, and then I want to get to 23, so I add 6. So the way I do the problem is I would leave it blank, get to the last instruction, and just calculate those out. And then set less than, and then T0 A2. We check to see if star first, which is T0, and second, which is A of 2, and then we branch not equal. And then we add our sum plus T of 3 because we get our value here. And then I increment T of 0 for 1 because that's star first equals star first plus 1, right? And then I do the last thing, I do this store instruction to update the pointer, so I store the value of T0 into A0 of A of 1, and that's how we maintain the integrity of that value. So your creativity challenge for this problem. Okay, so the rest of this that's due on Thursday is everything is through the end of section 5. You're going to create this test function where you're going to have like the same inputs. All you're going to do is you're going to change the values inside. You have to meet a couple of constraints that I've designed in the creativity challenge. So you can actually try to come up with your own problem And if you do that, you can get some homework points, and that'll be used to help you and your classmates prepare for the exam. So, does anybody have any questions on that? All right. Then in that case, you are dismissed.